Yeah.
How do you make the draft window so you can see the whole thing?
Where you can see the whole thing. Okay, so with this one, if I just hit, well, okay, here are your options. Let's do a quick review, a quick tour of the Zoom window. We'll just do parts of it. So if I do Zoom Standard, that's what I just hit. Zoom Standard takes us back to, if I hit Zoom 6, it takes the window back to its sort of original configuration, which looks like that, -10 to 10 on both axes, X and Y, right? If you want to do something different, let's say we wanted to look at our function on a specific domain, which a lot of times we do, right? A lot of times in math, we'll have an imposed domain, a restricted domain, so we'll just set the window up on that domain, but then we'll let the calculator control the range of the window, right? So let's say we wanted to look at these functions we're currently studying. Say we wanted to look at them from -1 to +2 for some reason. If I just hit graph, that's fine, we can do that. But if I'd rather spread the functions out so I can see them a little better because they're pretty compressed vertically, I can hit zoom 0. So that's going to take my chosen my chosen domain, right? The X values that define the window, and it's going to stretch the window out so the functions are represented throughout the whole window. Does that make sense? Okay. The one we did yesterday when we're inputting stat data, I think I've actually got some in there from yesterday. So if I do zoom 9, then the window is going to focus on, I think, okay, why did it just do that? How come it didn't go to the stat plot? Because it's not on, exactly. So if I turn the stat plot on, and now I go zoom 9, now the calculator will use the information that's stored in the stat editor, L1 and L2, and it'll size the window based on that. Okay? Then there's some other things that we'll talk about later, but like, what do you suppose zoom trig is? It has to do with trigonometry. And if I do zoom 7, I just want you to see what the size of the window is, because this is kind of cool. The window now goes from, that's different than I'm used to. I wonder why I did that. Strange. Zoom 7. That was the trig one, right?
Is this like necessary?
No, just useful.
Okay.
Yeah, the zoom trig one, I don't know why it does that. I'm used to it going 1, 2, 3, 4, 5. Oops. Huh. Never mind. I thought it was going to be really tricky and show you something really cool there, but that's a little strange. I'm not sure why it goes that far out. How come the X scale, here's one though. Okay, maybe I am being a little tricky. How about the X scale? Why is the X scale about 1.57? Ish. There's a good reason for it. What's with that decimal? Why would that decimal be important at all? What number do you think that might be related to? I'm gonna give you a hint, and this don't panic. I mean, we're not talking about this now, but just it came up with the Zoom stuff. What if I graph? And I know we haven't talked much about this at all, but let's graph sine x. Boy, that sine x function is really well represented. Look at how when I start right here with my sine function, look how it crosses the x-axis at all of those tick marks. So that x scale must have been chosen pretty well. In fact, there's one complete wavelength. Seems to be out there. 1, 2, 3, 4 tick marks. Anybody got an idea why that would be? Look at that decimal again. What's special about that decimal number? It's half a pi. Exactly. That's it.
Wait, which one?
It's half a pi. That's it. Yeah, I didn't think anybody's going to get that. That's pretty good. It's half a pi. And so as we'll talk about later this year, as we'll talk about later this year, the wavelength of a sine function is exactly 2 pi. And so look at that. See, it goes, there's half a pi, 1 pi, 3/2 pi, 2 pi. So when you hit zoom trig, it sets it up to play nicely with trig functions. Okay. But back to our, but I digress. Anyway, there's your Zoom tour for now. We'll do more later. There's some other stuff. When we get a chance, I'll show you other stuff. Let's go back to this though. So let's say we want to take our square root function, the blue one, and all I want to do is I want to flip it over the x-axis. How could I do that? What do I do?
Add a negative.
Add a negative? You mean
X.
make x negative, okay? So flip it over the x-axis. Let's try this. So you're saying I'm going to do, oops, gosh, what did I just do?
So you have to make the whole function.
Make the whole function negative. Okay, let's try that. So we're going to go negative, oh man, negative square root x, like that?
Yeah.
Okay, let's try that. Yeah, it worked, didn't it? Okay, that makes sense? What did we just do? We took all the y values that we were calculating, and multiplying by -1 just makes the y values negative but equal in magnitude. Does that make sense? So what if I wanted to reflect a function over the x-axis and stretch it by a factor of 2? What would I do? Multiply by -2, right? Okay, it works, right? Okay, so here's maybe the trickiest one yet. Now, you gotta really think about this one. How am I gonna take my original blue function and all I wanna do is reflect it over the y-axis? Ah, good. Does that make sense? Think about it. All I really wanna do then is in my function, I want the x values to be their opposites, but the y values to stay the same, right? Does that make sense? So all I'm going to do then is I'm going to go the square root of negative x. Okay, make sense? So what if I want to reflect it over the y-axis and stretch it vertically by a factor of 2? What do I do there? What would I do?
2 times the square root of x.
Yeah. Okay, then I'd put the 2 on the outside, right? Make sense? Okay, but now I got a different one for you. So you're right. I'm not going to do that one. What if I want to stretch a function horizontally? So now I want to just take the blue function. I'm going to clear out. We're getting too many of those things in there. Let's get rid of some of these. So what I want to do is I just want to keep the blue function normally aligned, but I want to stretch it horizontally by a factor of 2. Okay, how am I going to do that? That's tricky.
The square root of 2 x.
Yeah. Yeah. Right? So all I'm going to do now is I want to make the x's twice as big as they normally are, so I'm going to multiply the x by 2, and that's going to stretch it horizontally, right? So we can just go square root 2x and, oops, hang on. No, I got that backwards. Sorry, that's wrong. What do I do? I thought you were right, but no, that's not quite right. It's a little bit counterintuitive. What do you think? By half. Yeah, you multiply by half. Okay, makes sense? I can prove it. Let's look, it's hard to tell, but do you get a sense that that's been stretched by a factor of 2? Let's prove it though. I don't want you to take my word for it, I want to prove it. Let's graph the horizontal line y equals 1. And I'll show you another feature of the calculator while we're doing this then. Okay, so if I were stretching this, horizontally by a factor of 1, doesn't that mean that the places where those functions intersect the line y equals 1 would have to be, the blue one would have to intersect it with an x value that's half of the intersection of the red curve? Does that make sense? Let me make this a little bigger. I didn't say that very well, but somebody else say that better than I did. What's the purpose of the horizontal line? To demonstrate that we just stretched the function horizontally by a factor of 2. Why'd I do that? What do you think? Why'd I do that? Just gonna make the window a little bit different. You can see it a little better. What's the point of that horizontal line? How can I use that to demonstrate that the red one is stretched by a factor of 2? What do you think? Yeah, let's look at the intersections. So how do you find intersections? This is another thing that you'll be doing a lot of this on the calculators. So to find intersections, where do you think I'm going to go on my calculator to do something with the graphs? Yeah, which one? You remember which one has all the tricks for graphs? Second calc, right? Which one do I probably want?
Intersect.
Intersect, there you go, okay. But if I want to do an intersection, I have to be specific about which 2 curves I'm intersecting, right? You can only intersect 2 curves at a time. So notice that the calculator is asking me, what are the 2 curves? What's the first curve of the 2 that I'm intersecting? Okay, well, the first one in this case is y1, the blue one, right? So I can hit enter to tell them, yeah, that's it. What's the second curve? Is it the red one? It is. Oh, actually, no, it's not. Which one should it be? The black one. So I got to hit the down arrow and go to y3, which is 1, and it puts the cursor on the black one. And now I can say, yes, that is the second curve. And now it wants a guess. I don't even think you really have to provide a guess for something this easy, but all that really wants you to do is just take the cursor and put it over somewhat close to the actual intersection. So I mean, like right there is fine. Hit enter. And what do you know? The intersection is at 1, 1. Okay? Now I'm just going to find the intersection of the red stretched, horizontally stretched curve and the black line. So we'll do it again. Second, calc, 5. This time, y2 is my first curve, and y3 is my second curve. And I'm not even going to make a guess. I don't want it. I don't feel like it. And it told me the intersection is at 2, 1. X equals 2, y equals 1. There's my proof, right? So for equal y values, the x values were doubled. That's the same thing as a horizontal stretch, right? Make sense? Okay. And then, of course, if I wanted to also add a reflection to that, I would just make the x negative. So here's my challenge to you. So break out your notebooks. Here's what I'd like you to try to do. I would like you to... I want you to take the function f of x equals we'll just make it the square root of x. Why not? And I want you to do these things to it. I want you to, first of all, I want it to be shrunk horizontal or shrunk vertically. By a factor of 3, and then I want it to be translated 3 to the left, translated 2 up, and then, yeah, let's do that. So what's that gonna look like? All those things at once, in that order. If you want to consult with your neighbor, I'm okay with that. And if you need a calculator, anybody need a calculator? Come grab one. I got a bunch right up here. Come grab one if you need a calculator to kind of check what you're doing, to check your hypothesis. Okay, who wants to give this a try? Somebody want to come? You got a guess? Somebody? Tyler? You can inaugurate the pen. Come on up and draw what you think the function should be.
Worry about being
There you go. There you go.
You want me to just draw the function?
No, just write it. How would you make the function? Oh, it does that. There you go. Good.
Terrible handwriting.
It's all right. Not like mine. So, what do you think? You buy it? You buy it? Okay. All right, so here's the next challenge then. How could I tweak that function so that that whole thing is reflected about the y-axis? You might want to experiment on your calculator a little bit with this. A couple ways you can do a fraction. You can either just go, I'll show you. You can either, yeah, you can always, an easy way to deal with fractions, probably the quickest way to deal with fractions and the safest way is just to enclose them in parentheses. So I could always say something like that. And then that times something. Does that make sense? Then it treats it like a factor. But there's a tricky way on the calculator also. You can go, if you want the actual fancy fraction template, you go alpha F1, takes you to the fraction templates. And then you can just hit enter for number 1. Okay? Yeah.
The reason we have this is because we really took calculus at BMCC.
Mm-hmm.
They didn't accept the one from high school. And
They didn't accept the one from the,
so we had to retake it.
You're kidding me.
Over the summer. And apparently the teacher kept saying how she wished she could put fractions in on the calculator. And he's like, I'm just doing like that. And she was like astonished.
really?
So it's sort of like over the y-axis.
Over the y-axis, yeah. Okay, so what do you think? What's the verdict? Ruby, what do you think? What's your idea? How am I going to take that function y3 up there, same one that Tyler put up on the board, how am I going to take that and flip it, reflect it all over the y-axis? What was my recipe for flipping something over the y-axis? No. Let's see, I think it's up here. I don't know if I actually wrote it up there. We didn't. But how did we? We said to flip something over the x-axis, we just multiply the whole function by -1, right? No, we don't need to do any stretching, but I mean just the reflection part. What was it? Do you remember, Gabe, how did I flip something over the y-axis? Okay, you just multiply the x by -1. So now let's look at this. I want you to make a prediction then. Let's just try, let's run this experiment together here. What am I going to do to y3 then to flip this thing? That's the black one. How am I going to reflect that over the y-axis? What should it look like when I reflect it over the y-axis? Instead of starting there, it's going to start there, and it's going to open to the left or the right. What do you think? To the left, right? If I reflect that whole thing, it's got to be the mirror image, right? So what do you think? How am I going to do that? Negative sign in front of the x. Let's try that. And then we'll just see if we can explain what the result is. Let's try it. What do you know? What'd it do? Reflected it. How about that? All right, does that make sense? I mean, really, all we did there then is we just added the opposite values of, we multiplied each value of x that we were going to take. We just changed its sign, and so doesn't that affect the kind of change that we want?
Says error.
Right.
Yeah, my calculator might be.
It said error. I bet I know what you did. I bet you put a minus sign instead of a negative sign.
Oh,
Oh.
Tell me if I'm right.
It does the same thing.
no.
Those negative signs, the one down there.
Yeah, negative signs down here, exactly. This is the operation of subtracting. This is the negation of a value. All right, I think, we could play with this forever, but I think I'll just let you guys work a little bit on this. So the assignment is up.
6.7